Hello again, and we're going to do another problem with an inclined plane and also using Newton's laws of motion. Um, this particularly, it says Newton's second law here, but I would argue, I'm actually going to cross that out. No, I think it's Newton's first law. Um, and we'll see what we're given here. We're actually not given much. I don't have much room for that matter. We're given the free body diagram at least. So we don't have to worry about that one. We're also given the weight of the sled, and we're using force due to gravity, and the angle is given to us 30 degrees, and actually that's pretty much it. We're asked to solve for two things, and that is the tension and the magnitude of the tension, and the magnitude also of the normal force. I'm going to use capital N once again. Okay, and you see the reason I say that it's Newton's first law is that it even says it right here. These are the conditions for mechanical equilibrium, or specifically static equilibrium, because this entire sled is at rest. So it's not moving at all. It's being held together by the tension from the rope. And we're even saying that this is a frictionless slope as well. Okay? Now the formulas that we'll need okay, and so these are actually the formulas that we'll need. Simple as that. Okay, and this one's actually not too bad. It may look complicated, but once again, when you have an inclined plane, our coordinate system is also inclined as well at the same angle. But our angle, our theta, is actually right here. Okay, so the 30 degrees is between the negative y-axis and the axis and the weight vector. And so this is our x-axis and that's our y. Okay, so that actually puts us ready to solve it. So let's start with the x. So it's at rest, completely at rest. That means all the forces on it equal to 0. They have to cancel out because it's in what we call static equilibrium. Okay, so if you look at our free body diagram, there's only two forces in the x. Tension is going the positive x direction, and the negative mg sign, because this vector here is the same as this one right here, and that is actually opposite to the angle theta. So I have tension minus mg sine theta equals 0, or just simply move this to the other side, and I get that the tension, the magnitude of the tension already, is mg sine theta. And you can actually go ahead and solve for that already, but let's save that. And for the y, it's not accelerating in the y, it's completely at rest. And for the y, we have two forces as well, kind of similar. Normal force is going up, and the negative mg cosine theta is going down because it is adjacent to the angle. That's why it's cosine. Okay? So if you notice the pattern, it's kind of similar. Mg cosine theta is going down, and once again I'm going to take this term and move it to the other side. It's almost poetic. Similar. And even this mg here is actually already the weight. So you don't have to solve for the mass. You can just plug and check right here. Newton's sine of, sine of 30 degrees. And there, that should be 30.0 degrees. Okay, and that will give you half. Sine of 30 is a half, right? If you remember your unit circle, half of 77, which, looking at the answer key, there we go. And we're going to do the same thing for the normal force. Now for the normal force, we're going to expect something a little bit bigger, and sure enough, do 77 times cosine of 30.0. That's going to be square root of 3 over 2, or like 8, 6, something, I think. And sure enough, it gives us something a bit bigger than 38.5, almost 2/3 to be exact. And there you go, the magnitude of the tension that needs to hold the sled in place and the normal force. Now, what is this? It's a very simple problem, but what does that mean? Take note, the normal force here would have been more significant if there was friction holding in place instead of the tension, because the normal force is directly related to friction if there was, but in this case, it does not apply since it is a frictionless slope, snow-covered hill. So let's try another example later with friction. Okay? So you're just solving for the tension force and the normal force, the magnitude of those. The directions are given in the free body diagram. Make sure you have your free body diagram before you solve a problem like this, because it makes it a lot simple. Okay? Good luck and enjoy.